Hello students, so today we're going to look at the isomers of coordination compounds. So we know that isomers are compounds, two compounds or more than one compounds that has the same molecular weight, the same atomic composition, but different structures. So the structural chemistry of these compounds is a bit different in a way that they may have a branch structure or a long chain structure that actually differentiates these structures. However, these two compounds actually has the same atomic composition and same molecular weight. So if you look at isopropanol, okay, isopropanol is 2-hydroxypropanol. And if you look at propanol, okay, propanol, 1-propanol. So they are actually isomers in a way that they have the same atomic composition, the same percentage of oxygen, carbon, hydrogen, but the location of the hydroxyl group is different, where the hydroxyl group is positioned at carbon 1 in propanol, but in isopropanol, the position of hydroxyl group is on carbon 2. Okay. Now, there are two types of isomerism. There is the stereoisomerism and the structural isomerism. So the stereoisomerism differentiates the molecules by geometrical isomerism and optical isomerism. The cis and trans conformation falls under the geometrical isomerism. So if there is a compound like, for example, cis diaqua dichloroplatinum 2 and trans diaqua dichloroplatinum 2, these are geometrical isomerism. Okay, so because they have cis and trans, they are different by geometry. They have the same geometry, it's just that the position of the ligands, one is cis, one is trans, that categorize the compounds under the geometrical isomerism. Another isomerism that is classified under stereoisomerism is the optical isomerism. And we actually have learned this previously, where some compounds, they are enantiomers and diastereomers. So these enantiomers are usually chiral molecules. Okay, so because of their chirality, they can actually respond to optical light. And they have two conformation, the lambda and the delta conformation. So let's look at one by one example of geometrical and optical isomerism. The geometrical isomerism, there's cis and trans. Take into account two ligands that are positioned in 90 degree, okay, apart from each other. They are cis, while ligands, two same ligands that is 180 from each other is called trans. Okay, so we have also discussed about the facial and meridional. So to classify a cis and trans, we look at two identical ligands. If they are located 90 degree apart from each other, they are cis, while the trans will have a 180 degree. And the facial and meridional conformation, we have to look at three identical ligands. For example, A. If we look at A, okay, all these A ligands they are 90-degree away from each other. So this is the facial facial isomer. And if the A, okay, if the A ligands shows two 90-degree and one 180-degree separation, okay? So this A and that A is 90-degree away, and this A and that A is 90-degree away, while this and this is 180-degree. So that makes the conformation a meridional. So these isomers are meridional and facial depending on the position of the three identical ligands. Enantiomers are chiral. So because of their chirality, they actually rotate the polarized light. They respond to polarized light. Whenever they respond to polarized light, they will give the lambda or the delta. Okay, so they have to be chiral. So whenever you see a chiral compound, there usually are enantiomers of that compound. The other classification of isomerism is the structural isomerism. So there are 5 of them: linkage isomerism, coordination, ionization, hydrate, and ligand. So what are they? Number 1, the linkage isomerization. The linkage isomer is derived from the coordination atom of that ligand. Okay, so sometimes some ligands can have more than one coordination site. Some ligands has only one coordination site. Some ligands have 2 coordination sites, 3, 4, 5, and so on. Now take for example a nitro. Okay, a nitro ligand. If the nitrogen is the donor atom coordinating to the metal, okay, and at the same time, in another complex, the oxygen can also become the donor atom and coordinate to the metal. This is what we call linkage isomer, where one ligand can have different coordination site, okay, different coordination site to form coordination bonds. When nitrogen in nitro, when nitrogen coordinates to the metal, when nitrogen coordinates to the metal, this ligand NO2 will be named as nitro. But the same molecule, the same ligand, if the coordination happens through oxygen with the metal, this ligand will be named as nitrito. So when you see the nomenclature, it's written nitrito or nitro. This is indicating the coordination atom of nitro, NO2. Okay, the coordination atom of NO2. So look carefully at the nomenclature. If there's nitro or nitrito, it actually tells us that the metal coordinates to NO2 via N, or the metal is coordinating to NO2 via oxygen. The coordination isomer is, okay, let's look at this example here. Now it says here that some isomers differ in what kind of ligands are bonded to the metal and what kind of ligand is bonded to the metal of the outside of the coordination sphere. Now, when both cation and anion of a salt are complexes, the distribution of ligands between the two can vary. Now, you see, a simple inorganic salt, for example, potassium bromide. we have the cation and the anion, the potassium plus and the bromide, Br minus. Now in coordination chemistry, there's also cation and anion. It's just that the difference here now is the cation is no more like a simple potassium or sodium. It's more like a complex cation. And the anion is also a complex anion. So if you look at this example here, okay, the first example, let's look at the first example, this, right? And this. Now, if let's say we are given these two compounds and we are asked to classify whether they belong to the coordination isomer or what isomer, okay? Now, look at the metal center. Both compounds consist of cobalt 3, and you can also find cobalt 3 here. The first compound, cobalt 3, belongs to the cation complex, while in compound 2, cobalt 3 is anionic. It belongs to the anionic complex. In compound 1, chromium 3 belongs to the anionic complex and become part of the cationic complex in compound 2. So both of them actually have the same type of metal, but they become a different anion, a different complex ion. Okay, so in compound 1, what is becoming the cation now has become anion in complex 2, and vice versa. Now look at the ligand. The ligand, ammonia and cyanide. All right. So there's ammonia and there's cyanide in both compounds, right? In compound 1, the cation, which is cobalt 3, coordinates to ammonia, a neutral ligand. While in compound 2, cobalt 3 coordinates to cyanide, an anionic ligand. And in compound 1, chromium 3 coordinates to cyanide, but in compound 2, chromium 3 swap the ligand to ammonia. Now this is what we call coordination isomer. They actually retain the same type of metal, okay, the same oxidation state. It's just that the ligand now changes, okay. It doesn't actually change to a different kinds of ligand. It maintains the same kind of ligand, but a different coordination, okay, with the metal. That, let's say previously ammonia coordinates to cobalt 3. In second compound, ammonia now coordinates to chromium 3. So what is the name of this compound? So we know that for cation, the metal will retain its original name: cobalt, chromium, zinc, copper, nickel, titanium, vanadium. If the metal belongs to the anionic complex, the metal will be ended with ate, like platinate, nickelate, cuprate, ferrate, manganate, chromate, titanate, right? So this, for compound 1, we can name it as, cation first, followed by the anion. So because there's no other ligand, okay, coordinate to the cobalt 3, so this is hexaamine cobalt 3. And this, what about chromium 3 with 6 cyanide? So if we look at the oxidation state of both complexes, they actually carry, this is plus 3 and this is minus 3. Okay, so this is hexacyano. Now chromium here, because it is anion, belongs to the anion complex, so chromium here is chromate. Hexacyano chromate 3. So the full name here is hexaamine cobalt 3 hexacyano chromium chromate 3. Okay. Ionization isomer. Isomers with the same overall composition but contain different ions. Counter ions. Okay, counter ions. The ligand in the coordination sphere. What is the coordination sphere? The one in the heart bracket. The one in the heart bracket indicates the coordination compound. So those are in the coordination, within the coordination sphere. Those outside the heart bracket, okay, region, these are the counter ions that actually balance the oxidation state of the complex ion. The ligand in the coordination sphere and the ligand outside the coordination sphere is interchanged. Now, let's take, for example A. This is, there's ammonia and bromide. So, to name this compound, because ammonia now become amine, starts with A, so we name it as pentaamine bromo. Okay, what is the oxidation state of this cobalt? Sulfate carries -2. So the whole complex here is now +2. Ammonia is a neutral ligand, so it's a 0 charge. Bromide carries -1. So cobalt here is a cobalt 3. So the name, the nomenclature will be pentaamine bromo cobalt 3 sulfate. Now you see, the sulfate now has become the ligand in the coordination sphere. And the bromide here now become the counter ion outside the coordination sphere. Now, the interchange between these ligands makes it ionization isomer, makes the two compounds an isomer, an ionization isomer. What is a hydration isomer? A hydration isomer is when there's involvement of water. Water as ligand in the coordination sphere and water as the crystallization solvent outside the coordination sphere. So for example, in the first compound here, water is the ligand coordinating to chromium within the coordination sphere. It's hexaaqua chromium 3 trichloride. In the second compound, one water is dissociated from chromium, and that vacant spot is replaced by one of the chlorine that was previously outside the coordination sphere. That leaves 2 chlorine outside the coordination sphere. So now this has become penta-aqua chlorochromium. Chromium 3. Okay? Is it a chromium 3? You have to find out the oxidation state of chromium here, because in the second compound, the complex ion here carries a 2+ charge. So it makes the chromium here a chromium 3, because chlorine, okay, this chlorine is -1 in charge, and water is a neutral molecule, carries no charge. So chromium here is a chromium 3. Now pentaamine chlorochromium 3 dichloride monohydrate. Okay, So the number of water remain the same, the number of chlorine remain the same, the number of chromium remain the same, except that what was previously in the coordination sphere has now become the ligand outside the coordination sphere. And the ligand that was once outside the coordination sphere has now become the ligand within the coordination sphere. So the relocation of this ligand, as long as it doesn't change the ligand composition, it doesn't change the atomic composition, this is called isomer. And hydration isomer is the presence of water within the coordination sphere and outside the coordination sphere. The final isomer is ligand isomerism. The ligand isomerism is defined by the presence of the ligand itself that actually carries the same molecular weight and the same atomic composition. However, they possess a different molecular structures. Okay, for example here, number 1, the first ligand here is propylene diamine. Okay, propylene diamine. There are two amino group and a propane, a propyl chain in the middle. The second compound here retains the same number of carbon and hydrogen and 2 amino groups. It's just that it is a branch. Now it becomes a branch. Okay, it is no, the CH2 now is not the main. Okay, you see the first ligand here is just a straight chain, just a normal simple chain. Okay, where 2 amino group is located at the end of the chain. Okay, like this, for example. Okay, the end is here, 1, 2, 3, the end is here. Okay, so this is actually that. Okay, so what about the second compound here? The second compound here is this, your CH2. So you have N here. Okay, CH2. This is CH, where the CH has a CH3 here, and then there's an N here. Okay, CH2, right? You have CH2 here, CH, CH3, and N. So it becomes a branch structure. Okay, however, the molecular weight is the same. It just relocates the position of amino group. So this is also isomers with propylene diamine. Okay, both are diamine, but one is just a simple long chain and the other one is a branch structure. Now that is what a ligand isomer is about. So try this, right? Try to identify the coordination number. So the coordination number is the number of donor atom that contributes their electron that coordinates to the metal. Okay, not the number of ligand. Draw the chemical structure. When you draw the chemical structure, you have to make sure that you draw them correctly. Okay, so if the coordination happen through the carbon or the nitrogen or the sulfur atom, you have to show that coordination in the structure. Identify the category of the isomer. Okay, so what kind of isomer do you think this can have? Draw the chemical structure of the isomer, determine the oxidation state of cobalt in this complex and its isomer, and also give their nomenclatures. So try this and you may show your answers to me anytime.